In today's data-driven society, statistics have become increasingly prevalent. As a citizen in the present era, one is likely to encounter statistical methods in various aspects of daily information. However, the field of statistics is vast and complex, ranging from simple calculations of averages to advanced mathematical techniques studied at the graduate level. Consequently, individuals may struggle to discern which concepts are necessary for understanding specific applications. For example, as a cutting-edge subject, ChatGPT has made a significant impact as an application of natural language processing. Optical character recognition, OCR, and voice recognition are grounded in reinforcement learning techniques. Beyond these examples, contemporary research, technology, and even social activities necessitate a solid statistical foundation for those aiming to move beyond a mere cursory understanding. However, the connection between such research and concepts like average or the probability of dice, generally in the introductory chapters of statistics textbooks, may not be immediately apparent or intuitive. Therefore, this video aims to provide an overview of the statistical methods to facilitate their effective and beneficial utilization. Broadly, the users of statistics can be categorized into 5 different groups. As a user of statistics, the first step would be to understand that there are 2 concepts within the term statistics: descriptive statistics and inferential statistics, and to become familiar with the numbers that appear in descriptive statistics. Particularly standard deviation is a very fundamental concept, but there are cases where people get confused by the calculations and end up not understanding what is being done. Additionally, becoming acquainted with various types of graphs would also be appropriate at this stage. As the next step, it is considered to be at a level where one can understand the results of various inferential statistics and execute statistics using software like R or SPSS. This level involves understanding statistics with little or no reliance on mathematical formulae. Numerous books and resources adopt this approach to provide statistical knowledge for interpreting results and using statistical software packages. At this stage, it may be challenging to understand the procedures of inferential statistics, such as null hypotheses, p-values, etc., and various testing methods. The next level might be learning statistics using general knowledge level mathematics. When studying statistics at this level, books claiming to cover probability and statistics are likely to introduce the concept of probability. Initially, it might be challenging to move from thinking about probability as a mere matter of luck, to understanding it as a well-defined concept using formulae. Furthermore, one would likely attempt various calculations and inferential statistics by hand, which could lead to encountering some rather intricate computations. At a more advanced level, mathematical statistics incorporates university-level mathematics, including calculus and linear algebra. Individuals need to grasp concepts such as differentiation and integration, particularly for multiple variables, for example, partial derivatives, supported by a thorough understanding of limits, as exemplified by the central limit theorem. Linear algebra involves complex calculations, as it handles large amounts of data for multivariate analysis. The final level is concerned with whether to use measure theory, the Lebesgue integral, to define statistical concepts. Statistics using measure theory involve extremely rigorous mathematical discussions, and it can be argued that they are at a level best suited for those who create mathematics, those involved in cutting-edge mathematical research. However, in reality, the existence of measure theory is often hinted at in many mathematical statistics books, and it can also be encountered in more popular statistics books. Therefore, it is worth including the information for its potential significance. Furthermore, readers who want to deepen their understanding of concepts like the central limit theorem may find it worthwhile to take on the challenge. Now, I would like to go into a concrete explanation of statistical terminology and related theories, while actually looking at the map of statistics. The first encounter with statistics might be when we see numerical data presented in tables or similar formats. These tables may include values, mean, standard deviations, and other central measures. A mean, M, is an arithmetic average, which is the type of average we commonly use. Standard deviation, SD, is a measure of the dispersion of values from the mean. Descriptive statistics is the process of describing data characteristics using these values, such as averages and standard deviations. Now, let's consider the relationship between two sets of data, for example, the math scores and English scores of students in a class. We will determine if there seems to be a relationship between these two scores or not. Here, we introduce covariance and correlation coefficients. Covariance is directly calculated from the data, while the correlation coefficient converts the covariance to a scale from -1 to 1, allowing for comparisons across various data sets. A value of 1 indicates a strong positive relationship, meaning that students with high math scores also have high English scores. A value of 0 indicates no correlation, and -1 indicates a negative correlation. Graphs are essential for making the results of descriptive statistics more accessible and easier to understand. There are various types of graphs, such as histograms, pie charts, box plots, and line charts, each suited for different applications. Histograms display data distribution, pie charts represent proportions of categories, box plots illustrate data spread and skewness, and line charts demonstrate trends over time. The perception of numerical information can be influenced by the way visual information is presented, which can sometimes lead to impression management. Impression management involves the deliberate manipulation of visual representations to shape the perception of data. In everyday situations, this might occur when a company manipulates the scale or layout of a graph to make their sales growth seem more impressive than it truly is. From here on, we will not only focus on summarizing data but also explore statistical estimation using the data. Before diving into each statistical method, I would like to touch upon the concept of statistical hypothesis testing. For example, when comparing two data sets, what we want to investigate using statistics is whether there is a difference between the two data sets, such as whether a class that employed a certain teaching method had better results compared to a class that used a traditional teaching method. However, when addressing the question of whether there is a difference, the issue of how much difference there is arising, making it difficult to handle. Therefore, the initial process involves setting up a problem that assumes there is no difference in the data, and then demonstrating that this is very unlikely to occur, ultimately indicating that there is a difference. This estimation that there is no difference in the data is called the null hypothesis, and by deeming this null hypothesis implausible or rejecting it, we can conclude that the initial claim of there being a difference is likely to be true. Now, there are several points to consider in the interpretation of this hypothesis statistical test. First, regarding whether to reject the null hypothesis or not, we use the p-value as the significance probability, usually set at 1% or 5%. Even if the null hypothesis can be rejected in the calculation, there is still a possibility that the null hypothesis is correct. This mistake of concluding that there is a difference in the calculation when there is actually no difference is called a type I error or alpha error. Conversely, if the calculation concludes that there is no difference when in fact there is a difference, this mistake is called a type II error or beta error. It is not possible to eliminate these errors, and since each error has a trade-off relationship, where to set them becomes another issue. The use of deviation values in tests can be considered an interesting example of utilizing means and standard deviations. Deviation values involve scaling the obtained values by setting a specific value, such as the most basic z-score, where the mean is set to 0 and the standard deviation to 1. This allows for the evaluation of scores given in different standards to be assessed on the same scale. After calculating deviation values such as z-scores, the normal distribution is often used as a criterion to measure the ranking of the obtained values within the overall population. The normal distribution is a distribution that shows the number of people who have a certain deviation value. Its shape is characterized by a bell curve centered around the mean. If we consider the total population as 100 people, in the case of z-scores, approximately 34 people will score between 0 and 1, 13 to 14 people will score between 1 and 2, 2 to 3 people will score between 2 and 3, and at most one person will score higher than that. Some people may wonder why these numbers have such values, but this can be attributed to advanced mathematical calculations, so please understand that this distribution takes the form of a normal distribution. Additionally, some people may not grasp why the normal distribution is a smooth curve, but if you think of a histogram and gradually refine it, it can eventually be seen as a curve. In actual statistical tests, the t-test is used to compare two groups, while ANOVA is used for comparing three or more groups. ANOVA shows that the three groups are not equal, so if you want to compare each group, you will need to continue with further statistical tests. However, when comparing each pair of groups among three or more groups, simply using the t-test increases the probability of errors. As a result, you cannot proceed as is. Instead, you need to use corrections like the Bonferroni method or employ methods like Tukey's test for multiple comparisons. So far, the tests mentioned have been parametric tests, but for non-parametric group comparisons, there are the Mann-Whitney test, Kruskal-Wallis test, and Steele-Dwas test, which are the non-parametric equivalents of the t-test, ANOVA, and Tukey test, respectively. Another frequently used non-parametric test is the chi-square test, which examines whether the frequencies of each element are biased by utilizing cross-tabulations. Regression analysis is a method used to find an equation that estimates the values of one dataset from the values of another dataset, and then determines how accurate that estimation is. The simplest example would be when there are sets of values for x and y, with the equation being y equals x plus b, a and b can be determined as specific numbers through calculations. For example, suppose the result of a math test score is found by doubling the score of a science test and then subtracting 15 points, that is, math equals 2 times science minus 15. To elaborate further, calculating these 2 and minus 15 coefficients is called regression analysis. When a large amount of data is collected in a study and a large number of variables are handled in the model, various results can be obtained by using various methods called multivariate analysis. Multiple regression analysis is an extension of the previous single regression analysis and uses more values to derive estimates. Factor analysis is a method to find several factors underlying a large number of factors. Discriminant analysis is a method to determine which group an element belongs to. Cluster analysis is a method of grouping elements based on their distance from each other. Principal component analysis is a method of finding factors that contribute more to the explanation of the data. Other techniques involve quantification, which allows the statistical analysis methods discussed so far to be applied to both quantitative and qualitative data. Additionally, path analysis and structural equation modeling, SEM, are used for more complex models. From here on, we will explore the methods of statistical theories using mathematics. Some people might find the subject to be suddenly difficult when mentioning mathematics, so I'd like to provide explanations for some mathematical symbols and concepts as well. When studying statistics in mathematical formulas, it's common to start with counting techniques, specifically permutations and combinations. This foundation is important because probability is calculated by dividing the number of desired outcomes by the total number of possible outcomes. To accurately determine probabilities, one must be able to compute the various possible patterns that can occur. The symbol sigma simply means the sum of all elements, making it much easier to represent the sum of thousands or tens of thousands of elements than listing them one by one. You may also notice that the button for calculating the total in Excel is represented by sigma. Variance and standard deviation are measures used to represent the dispersion of data, indicating how far individual data points are from the mean. They help assess the spread of values within a dataset. Variance is calculated by taking the following steps: 1. Subtract the mean value from each data point. 2. Square the differences obtained in the previous step. 3. Calculate the average of these squared differences. Squaring the differences is necessary because simply summing the differences would result in 0, as positive and negative values would cancel each other out. Additionally, using squared differences ensures positive values, making the calculations less complicated. Standard deviation might appear complex due to the presence of a square root. However, the square root is applied to adjust the scale of the measure because variance calculations involve squaring. By taking the square root of the variance, the standard deviation is expressed in the same unit as the original data, making it easier to interpret. As we advance in our study of statistics with a mathematical approach, one of the first unique formulas we may encounter in probability theory is the formula for conditional probability. Conditional probability helps us understand the likelihood of an event occurring, given that another event has occurred. It is often represented as the probability of A given B, which denotes the probability of event A happening given that event B has occurred. The formula for conditional probability can be written as P of A given B equals P of A intersect B over P of B. Here, the probability of A intersect B represents the probability of both A and B happening, and probability of B represents the probability of B happening. For beginners, it might be challenging to understand how the elements on the left and right sides of the equation correspond to the elements in the fraction on the right side. A Venn diagram can be a useful tool for visualizing the formula. In the Venn diagram, the denominator, the probability of B, represents the total elements in the condition, event B, while the numerator, the probability of A intersect B, represents the relevant elements under the condition, the intersection of events A and B. This visualization can make the concept of conditional probability more intuitive. It's essential to understand conditional probability, as it forms the basis for Bayes' theorem, a key concept in probability statistics. Thus, it is well worth taking the time to learn and remember this formula. Given that it is impossible to reduce both alpha and beta errors to 0 in a hypothetical statistical test, we can use this fact to determine the test's accuracy and the number of samples needed to achieve the desired level of precision for the target statistic. The precision of a statistic is referred to as the power of the test, 1 minus beta, and since it is not possible to eliminate all errors, it is crucial to balance the power with real-world constraints. For example, if a sample of hundreds of thousands could be obtained, the test's precision could be maximized. However, this may not be feasible in many research contexts, necessitating the identification of a variable that allows for meaningful results to be obtained in a realistic manner. The formulas for both parametric and non-parametric tests discussed in the previous section are provided. It is important to note that the presence of sigma in most of these formulas indicates their additive nature. This means that each formula consists of a series of straightforward calculations, though the quantity of these calculations can be large. Essentially, each formula is a cumulative sum of numerous simple calculations. In the case of single variable regression analysis, instead of finding various constants using the least squares method and partial differentiation, we calculate the mean, variance, and covariance of two variables to determine the slope and intercept. I recommend that readers refer to their textbooks for concrete examples. Reviewing examples with actual numerical values can be particularly helpful. For individuals who have reached this level in search of mathematical techniques, I believe they can expand their knowledge through various books on the subject. For those not looking for in-depth information, let's briefly examine what mathematical statistics cover, in general. Before diving into actual calculation examples, I would like to touch on the necessary tools, differentiation and integration. Essential tools in higher mathematics, differentiation and integration are indispensable. Differentiation involves focusing on a single point on a curve, zooming in on it, and magnifying it to an extreme degree. At this level of magnification, the curve appears more like a straight line. This method makes it easier to handle complex curves by transforming them into simpler forms. For a more relatable example, we all know that Earth is round, or curved. However, when we view it on our scale, we perceive the ground as flat, like a plane or line. In the context of graphs, the slope of the magnified straight line becomes the slope of the tangent, making differentiation a useful tool for finding characteristic values like maximums and minimums. Integration, on the other hand, is the operation of returning the characteristics found on the infinitesimally small scale of differentiation back to the original scale. In terms of graphs, integration corresponds to the area between the curve and the axis. If the function being integrated represents a probability curve, the integrated area becomes the probability, making integration a crucial calculation. In mathematical statistics, it is necessary to calculate sigma and integration to determine values such as expected values. For instance, sigma is used to calculate the total probability of a discrete probability distribution, which equals 1, while integration is employed for continuous probability distributions. Moreover, both the expected value and variance can be derived using summation sigma and integration methods in a similar manner. The moment-generating function is a technique used to compute basic statistical measures, such as mean and standard deviation, in a more general way. By incorporating the concept of moments, we can categorize these measures as follows. The mean is the first moment, the standard deviation is the second moment, skewness is the third moment, and kurtosis is the fourth moment. To calculate moments, we use different functions depending on the context, such as the moment-generating function, probability-generating function, and characteristic function. Additionally, differentiation and integration are employed in the calculations. One symbolic example is the use of a technical method called Gaussian integration to show that the total probability of a normal distribution is 1. Gaussian integration is the integral of e to the power of negative x squared dx equals the square root of pi. Central limit theorem states that even events following various complex probability distributions can be considered as normal distributions when the sample size is large. By utilizing this theorem, various statistical processes can be performed using the well-known normal distribution. Regarding statistical hypothesis testing, as long as we understand the probability distributions mentioned earlier, it should be possible to perform calculations. However, as an extension of this, rather than simply deciding whether to reject or accept the null hypothesis based on the p-value, we can consider the range of values in the population from which the p-value can be derived, which is called the confidence interval. Using mathematical statistics, we have developed a range of methods to estimate population statistics based on sample distributions. After obtaining these population estimators, it's crucial to evaluate their accuracy in relation to the best possible estimation. To assess this accuracy, we use a concept called effective estimators, and numerous methods have been proposed to calculate them. Such approaches include Fisher's information and the Cramer-Rao equation. Partial derivatives are required for calculations. Variable transformations are frequently employed to derive probability distributions. To integrate a function that involves these transformations, the substitution integral technique is often employed. This technique can be extended using the Jacobian determinant. As the Jacobian is a matrix, it is essential to be familiar with matrix calculation methods. When you square multiple standard normal distributions, mean of 0, standard deviation of 1, you get a chi-squared distribution. Dividing a chi-squared distribution by a standard normal distribution results in a t-distribution. For two chi-squared distributions, divide each by its own degrees of freedom and take the ratio of the two resulting values to get the f-distribution. This helps to explain why t-distributions are used for comparing means in t-tests, and f-distributions are used in ANOVA tests that analyze sums of squares. The normal distribution appeared in the estimation testing section, but of course, the model distribution is not limited to this, and there are various distributions, some of which involve quite intimidating equations. However, by capturing the relationships between them, we can likely deepen our understanding of various probability distributions. Examples include the uniform distribution, Bernoulli distribution, Poisson distribution, binomial distribution, t-distribution, f-distribution, beta distribution, gamma distribution, and Weibull distribution, among others. It is recommended to refer to textbooks and other sources for each of these distributions. The beta and gamma functions, which are key components of the beta and gamma distributions, can be somewhat complex. To better comprehend these functions, it is helpful to know that the gamma function serves as an extension of the factorial concept, while the beta function is closely related to a specific integral formula that is employed to calculate the area enclosed by a quadratic curve, based on the coordinates of the intersection points. When the number of variables and equations used in statistical analysis increases, it is beneficial to have a method that allows for calculations with a set of numbers, rather than performing them individually. For instance, when considering simultaneous equations, it is possible to represent not only the equations themselves but also the matrix of variables and the matrix of coefficients. The advantage of matrices is that they provide a well-established method for solving equations, changing axes, rotation, and so on. Matrices are also useful for describing probabilities of transitions between states, such as in Markov chains. When performing regression analysis, the goal is to create a model function that best represents the relationship between variables. To achieve this, we calculate the difference between the observed data and the values predicted by the model function. The least squares method is employed to find the coefficients that minimize this difference. Since this difference is expressed as a function, differentiation is used to locate the minimum point. In more complex cases, such as multiple regression analysis or other multivariate analyses, matrices are employed to organize and process the data. Matrix calculations can be more challenging than basic arithmetic operations due to additional constraints. However, they form the basis for valuable analysis techniques. As a result, it is worthwhile for readers interested in understanding the underlying mathematics to explore matrix operations. Mathematical techniques play a crucial role in demonstrating the effectiveness of different statistical models. Methods such as the Achaik Information Criterion, AIC, and the Bayesian Information Criterion, BIC, rely on values like maximum likelihood and the number of parameters derived during calculations to identify the most suitable model among the candidates considered. In Bayesian inference, methods such as MAP, maximum a posteriori, and MCMC, Markov chain Monte Carlo, are well known. These theories involve the application of various probability distributions in a mathematical context, with complex distributions such as the beta distribution and gamma distribution being used in practice. Other commonly heard statistical analysis methods include time series analysis, stochastic processes, and neural networks. Please refer to appropriate reference materials as needed. By redefining probability statistics using measure theory, we can manage objects that cannot be handled with traditional mathematical concepts such as Riemann integration. Riemann integration is a classic method for calculating the area under a curve, but it has limitations in handling certain functions. Measure theory allows for a wider range of applications by introducing the concept of a measure, which is a method for calculating the weight of each value within the whole. By considering these weights, we can treat outliers in real data as values with no weight, or zero, allowing us to calculate the main trends without being influenced by a small number of outliers. This concept is referred to as almost everywhere. One notable example is the Dirichlet function. Using this measure to perform integral calculations is called Lebesgue integration, which also requires sigma algebras and Lebesgue measures. The Lebesgue integral is easier to work with in terms of limits compared to the Riemann integral, and it also allows for the easier interchange of the order of integration. This interchange is facilitated by Fubini's theorem, which states that under certain conditions, the order of integration can be switched. Therefore, measure theory is likely to be well suited for probability and statistics, which involve handling limits. These theories have practical applications in fields such as machine learning and natural language processing. For readers interested in the technical background of these fields, exploring these concepts may be worthwhile. This video aims to serve as a valuable guide for non-experts in statistics by offering a comprehensive overview of the field in the form of a map, and clarifying the complexity of various statistical concepts and terminology commonly encountered in research. Readers can use this guide to determine the level of statistical knowledge they need to acquire or to better understand the context in which certain concepts are used. Ultimately, this video seeks to promote research activities by fostering a deeper understanding of statistics. Although statistics is an extensive and highly complex field requiring applied mathematics, it can be difficult for individuals who are not specialists to grasp its intricacies. However, by adopting a high-level perspective and viewing statistics as a practical tool, individuals can use it to their advantage and contribute to the field's overall development, a highly rewarding endeavor for all involved.